In this problem, we are discussing the Cantor-Bendixson theorem in this problem, which basically decompose any subset of the real line into a perfect set and a countable set. Okay, and the way to do it through what's called condensing point. Okay, so what is a condensing point? So we have so let a subset of R. So A is a condensing point of A for every epsilon, A minus epsilon, A plus epsilon, the sect A is not countable. Obviously, if A is a condensing point of A, then A is an accumulation point of A. Okay? The converse is not true. Okay? So for example, if we take A equal 1 over n greater than 1, then 0 is an accumulation point of A, but A has no condensing point since it is countable. Okay, since A is countable, you cannot have a condensing point. So we have to be very careful. Okay, this concept of condensing point is stronger than accumulation point or limit point. Okay, so consider P. So these are the condensing points of A. Then either P is empty or P is perfect. Okay, so assume P is not empty. Okay, and let us prove that P is perfect. Okay, for that, what we're gonna do is let F be the complement of P. Okay, so we claim, as we'll see at the end of this problem, that F is countable. F is countable. How do we prove that? Let A belongs to F. Of course, assume that if it's empty, then it's countable. So assume F not empty. Let A belongs to F. Then A is not a condensing point of A. So there exists epsilon positive such that A minus epsilon, A plus epsilon intersect A is countable. Okay? So now what you do, here is A. Here is A minus epsilon, A plus epsilon. Let us take, because we want countable, okay? So we're going to take two rationals, R1, R2, like this. So then we choose R1. So we are choosing R1 and R2 in Q. This is by density of the rationals, such that R1 is between A and A minus epsilon, and R2 is between A and A plus epsilon. Obviously, the interval R1, R2 intersect A is countable because it's smaller than A minus epsilon, A plus epsilon intersect A, right? And A belongs to this interval, okay? I mean to this intersection, sorry, to this intersection. Great, so now this tells me what? That F is included in the union of, these sets in R1, R2 intersect A, where R1, R2 belongs to Q, okay, R1 less than R2, and such that the intersection of R1, R2 intersect A is countable. Okay? So now what happened? What do we have here? This set is countable. This set is countable. So we have a countable union of countable sets. Therefore, F is a subset of a countable set. Therefore, F is countable. Great. So now let us prove our claim that P, now we're ready to prove that P is perfect. So we want to show that we want to show that P is equal to P prime. Okay? Let P belongs to capital P. So we want to show that P belongs to P prime. So we know, so P is a condensing point of A. So for every epsilon, okay, the set P minus epsilon, P plus epsilon intersect A is not countable. It's infinite, not countable. Okay? Since that's where we are going to use the set F that we did before, P minus epsilon, P plus epsilon intersect A is in fact P minus epsilon, P plus epsilon intersect P union P minus epsilon, P plus epsilon intersect F. So this set is countable because F is countable. And this set is uncountable by definition of condensing point. Therefore, P minus epsilon, P plus epsilon intersect set P is not countable. Okay? And which means that P is a condensing point of P. So P is also an accumulation point of P. In other words, P belongs to P prime. Okay? Conversely, okay, assume P is an accumulation point of P. P belongs to P prime. Okay? Then let epsilon positive. Okay? So we know that P minus epsilon, the P plus epsilon intersect P has an element, in fact has infinitely many, but an element P bar belongs to P different from P. Okay? Now, again, because P minus epsilon, P plus epsilon is an open interval, we can find delta such that P bar minus delta, P bar plus delta is in P minus epsilon, P plus epsilon. Okay, but now we know that P bar is a condensing point of A. So P bar minus delta, P bar plus delta intersect A is not countable. Okay, since this is smaller than P minus epsilon, P plus epsilon, okay, is not countable. So this one is smaller, than this one, okay? And therefore, if the smaller one is not countable, the bigger one is not countable, which means that P is a condensing point of A, which implies that P belongs to P. So we have P prime subset of P, P subset of P prime. Conclusion, P is equal to P prime. In other words, P is perfect. So our proof shows that any set, any subset of R, the proof that we just did shows that for any subset of R, C is equal to a union of a perfect set P, which may be empty by the way, and a countable set.